How you doing? I'm Mr. Rose, and today we're going to continue to talk about rotation, specifically kinetic energy of rotating bodies. So here I have drawn three masses, mass 1, mass 2, mass 3, rotating about some axis. And they're all rotating about this axis as if they're rotating on one rigid body. So what I'm going to do here is I'm going to connect. So I have distance R1, I have distance R2, and I have distance R3. Things that I know about this system. I know mass 1 does not equal mass 2, nor does it equal mass 3. And I know that R1 does not equal R2. That also does not equal R3. So what are some commonalities? Well, I know, again, if we're all rotating about this axis, since all of my radii, or my distance from that rotation, are different, I know each one moves with a different translational velocity, v1, v2, and v3. And I also know that those are not equal. What is equal about it, however, is omega. Its rotational velocity of each one is the same. So we learned how to calculate these translational and rotational velocities. I know v1 is equal to my rotational velocity omega times r1. I know v2 is omega r2. I know v3 is omega r3. Now, since they're in motion, if I wanted to calculate their velocity, I know that's kinetic energy. I know kinetic energy equals 1/2 mv squared, and I know kinetic energy, just like every energy, is a scalar quantity. Thus, I find the kinetic energy of that one, plus that one, plus that one. That's the kinetic energy of my entire system. So I know my kinetic energy is 1/2 times the sum of my mass times velocity squared. Doesn't matter how many masses and how many beats. All of those live together. I know now, though, that as this rotates, for this rotational motion, as the whole system is rotating, this mv squared is really omega, my angular velocity, times r, how far away it is from that center of rotation, squared. So my kinetic energy is actually, for this rotating system, kinetic energy is 1/2 omega squared. They all have the same omega, all the same angular velocity, times the sum of all of the masses times how far away they are. It's really just a simple substitution. The question then becomes, what is mr squared? That's different for every single system here. What is that, and how do we calculate that? Well, the sum of mr squared, it tells us something. What it's telling us is it's telling us the mass distribution for some rigid body rotating about some axis. In other words, this is something that we know as physics as the moment of inertia. We know inertia is an object's ability to resist a change in motion. It's straight from translational kinematics. Well, now it takes energy. It's hard to get something to spin, get something to rotate. So rotational inertia is just that. Its moment of inertia is just that. Its moment of inertia is the ease of which it's spinning. Is it spinning? Is it hard to spin? Is it easy to spin? Which means I, if I can see, mr squared, has a unit of kilograms times meters squared. So my kinetic energy of a rotating object is 1/2 I omega squared, where I is just the sum of all the masses times the radius squared. I'm not sure if that's coming out. mr squared. So this brings me to one of my favorite examples, something spinning around in a circle. Hold right there. So one of my favorite examples, I'm sitting in one of a very classic spinning chair, very expensive physics equipment here. If I spin myself around in a circle, as I spin, my mass is obviously going to stay the same. But what I'm going to do is I can change my radius. I can change how big I am spinning around. And we should know that with my arms spread out, I should spin slower than when my arms are close together. So as I try and spin myself, slowing down, speeding up. Let's see if I can do that again, because I kind of went off camera. Faster, slowing down, and speeding up again. So you, I'm sure, have done this. All of us have done this, and you see it in ice skating all the time. A big axis means they spin around slower. Bring their axis in means we spin around faster. In other words, it's easier to spin. My moment of inertia, or I, is much smaller than when I have a large radius. So now that I stopped spinning around, I can focus, and I can say that that spinning around example tells us that the moment of inertia, I, is focused. It is focused about some axis of rotation, some fixed point. So if I change that axis of rotation, for example, the example I drew up here, if I move my axis of rotation from, say, where I put it, I labeled that wrong earlier, that should be R3. If I move my axis of rotation to mass 3, so now everything is, say, spinning around mass 3, what that means is my radius over at mass 3 is 0, and I don't calculate that. I can't bring it into my calculation for rotational kinetic energy, because now everything is spinning about that axis. What I want to continue with this conversation is actually a small little sidebar and continue our language or our translations. In other words, what do we know so far? We've learned a lot of physics, and we learned a whole lot about translational motion. And all of that translates, no pun intended, into rotational motion. So things that are linear, traveling the xy axis. I just picked my favorite equation, d equals v naught t plus 1/2 at squared, to represent all of our kinematic equations. All of those translate or move into a rotational rotation. Theta minus theta naught equals omega naught t plus 1/2 at squared. We now know there's some kinetic energy, linear translational kinetic energy, 1/2 mv squared. Well, it also takes energy to rotate or to spin about some axis, 1/2 I omega squared. If I look at that, that must mean that my mass equivalent rotationally is I, and that makes sense because mass is inertia. We talk about Newton's first law, an object in motion stays in motion, an object at rest stays at rest. It's related to an object's mass, or it's known as the law of inertia. Well, if I have a mass and a velocity, I know I have some momentum, P equals mv. We haven't done this yet, but I can clearly just make straight substitutions, and I can say this is translational momentum. Angular momentum, L, is equal to I times omega, our rotational mass equivalent times our rotational velocity equivalent. Well, we also know that Newton's second law, F equals ma, is really a momentum law. So if there's a momentum, an angular momentum, mass times velocity, and an F equals ma, that also must mean in chapter 10, we're going to get to what Newton's second law is rotationally. It's our change in angular momentum per unit time, just like this is our change in momentum per unit time, is really just I times alpha. Newton's second law only in rotation. That's a little preview of what's to come. To continue this conversation, however, we're going to talk about calculating moments of inertia. So a moment of inertia, I, is constant for every kind of shape. In other words, a solid sphere has a constant rotational inertia, I, about its center of mass. It's something we can look up. You in your textbook have them on page 291. If you don't want to look at your textbook, you can just Google moments of inertia, different shapes, and you can come up with a list of images that's probably 3x3 or 4x3 of a whole bunch of different shapes with different moments of inertia. What if you don't have that and you need to calculate it? Need my demonstration here. If I want to calculate the moment of inertia, I'm going to use this simple equation that we've already seen. I is equal to the sum of every little mass times the radius squared. Well, we know that when I see the summation sign, I can throw in some calculus here. And I can say that I want to take a differential mass unit about how far away it is and integrate or take the sum of all of those units with my antiderivative. Well, this would be if it's rotating about its center of mass. Nice and easy. I know what you're thinking. You're thinking, what if I'm playing baseball? I don't swing a baseball bat about its center of mass. I swing a baseball bat from the end. So if I need to swing and calculate that moment of inertia about some axis that's not through the center, how do I do that? Well, we do that with something that is called the parallel axis theorem. The parallel axis theorem, I usually don't do this. I'm going to read this straight to you. Relates rotational inertia about any body, about an axis through the same body, about any point that is parallel through that is a parallel axis through its center of mass. What does that mean? Well, here I have my object. We'll call this a uniformly mass length rod of mass m. We'll say it's spinning about its center of mass L, so it's rotating like so. If I want to know its rotational inertia I about its end, what I do is I have some perpendicular distance, as I have my definition, some perpendicular distance about its center of mass, as long as the axes of rotation are parallel. Here's my axis of rotation, here's my axis of rotation. Those two rotations are parallel, so I can calculate my moment of inertia through the parallel axis theorem by I, the center of mass, what's easy to calculate, plus m, the mass of my entire object, times d squared, where d is the perpendicular distance from that center of mass to my new point of rotation. Let's do an example of both. Okay, so here I have my example set up behind me. I have some uniform rod of length L. I'm going to call it a mass of m, and like I said, it is a uniform mass distribution. If I wanted to know its moment of inertia I about its center of mass, or if I was given its moment of inertia I equals 1/12 ml squared, and I needed to prove it, it's a really simple calculation. So what we're going to do is we're going to use our I equals r squared dm. That is, I'm going to take the antiderivative of r squared times my differential mass unit dm, and I'm going to integrate that. But I see a problem that we've seen before. dm is clearly not the same thing as r, so I can't just take the antiderivative of that. So what do? First, I'm going to set an axis. I'm going to set this an x-axis here, and now it's rotating on my x-axis in like kind of that helicopter fashion. And I'm going to take my segment here, dx, or dm rather. I'm going to say dm is going to be constant per differential mass length dx. And what I can do by that is the same trick we've done in the past. I'm going to relate dm, my differential mass unit, to my now differential length unit, dx, which means I can set up a ratio or a proportion. I can say my mass element, dm, divided by my length element, dx, is equal to the total mass divided by the total length, m over L, which means dm is really equal to my total mass, L, times my divided by my total length, x, multiplied by every small segment, dx. Put that into my antiderivative. I have I equals r squared dm. That's really x squared, where my different lengths are, right? I'm going about my axis. My different lengths, I put it on the x-axis. X squared times dm, mass divided by length, times dx. Now I know I can take the antiderivative of that. X and dx and m and L are constants. So my mass and my length come out of my integration, and I'm left with x squared dx, which we've done before. The antiderivative of x squared is 1/3 x cubed. So I'm left with m over 3L times x cubed. And my limits of integration, which I hadn't put in here, are from negative L over 2 to L over 2, my entire length of my rod, from L over 2 to negative L over 2. So 2 to negative L over 2. So I have L cubed over 2 subbing in, minus a negative L cubed over 2. That whole thing is cubed. I do out my math. Minus a negative comes to a positive. L cubed over 8 plus L cubed over 8 times m over 3L. That shows, through simple algebra, that my moment of inertia about the center of mass is 1/12 ml squared. Well, going back to that baseball bat, what if I needed to know the moment of inertia I about the end? Well, I would use now the parallel axis theorem. I know that the I, moment of inertia about the center, is 1/12 ml squared. I know that my axes of rotation are parallel, and I know that it's separated by a distance, L over 2. I'm going to plug into my new parallel axis theorem, I about the center of mass, plus the total mass times d squared, how far away it is on a perpendicular distance. What we just proved, I is 1/12 ml squared, plus the total mass m, how far away it is, L over 2, that whole thing is squared. I have 1/12 ml squared plus 1/4 ml squared. That would be 1/12 ml squared plus 3/12 ml squared, which would be 4/12, which reduces. I is equal to 1/3 ml squared. This is the moment of inertia about any thin uniform rod with its rotation about the end as opposed to about the center. You could also do it a longer way, but the parallel access theorem is a shortcut. It's a much better, easier way. That's all I have for you today. If you want to just wait just one moment. Physics puns. Please feel free to like, click, or subscribe. Keep your questions coming, and I'll see you next time.